Good evening, everyone. Good evening, good evening, good evening. I welcome you all again to the JEE Enthuse. Hope all of you are doing great, having the wonderful time. Well, people, if I'm audible and visible to everyone, hit the chat box with the thumbs up. Yes. Hit the chat box with the thumbs up if I'm audible and visible to everyone. Yes. Good evening, Kirito. Good evening. Hi, Devil. Hi, Darshini. Hi, Cool Girl. Hi, Janan. Hi, Nishant. What's up? Janan is saying Wassim Sir's army is back. Welcome, Janan. Welcome. Hi, Darshini. Good evening. Good evening. Hi, Yogesh. I'm doing wonderful. How are you doing? Good evening, Nishant. Good evening. How are you? Hi, Shreya. Hi, Ashwarya. Good evening. Good evening. Good evening. Good evening. Welcome to the session, guys. Welcome to the session. All right. As you all must be knowing, we are left with one session. We are left with one topic from the chapter Chemical Equilibrium, that is your Leachate layers principle, which we are going to cover in the today's session. Yes, yes. Navneet has come up with the quote, never regret anything that made you smile. Oh my God. Oh my God. Yes, Kiran, Hadi was from NEET Elite channel. Yes, 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 yes. Welcome, Anurag. Welcome. Welcome, Jumana. Welcome, welcome, welcome. So people, let's get started with the today's session, okay, in which we are going to cover the Leachate layers principle, which is again the most important topic from the chapter Chemical Equilibrium. Yeah. Okay, so before starting the session, let me introduce myself. As you all must be knowing, my name is Wassim Sir and I'm your chemistry master teacher right here. Okay. So people, this is the schedule of the week. You can have a look on it. Okay. In the today's session, we are going to do the chemical equilibrium last session. Tomorrow, we are going to start the ionic equilibrium, guys. Yes. Tomorrow, we are going to start ionic equilibrium. And in this whole week, we'll be covering the whole ionic equilibrium in detail, right? Yes. All right, people. Talking about the mentee sessions, as you all must be knowing, on Tuesdays, you have got the mentee session with the Shmon Sir. Okay. Thursdays, you have got the mentee sessions with the Shreya Sir. And on the Sunday, you'll be having the mentee session with me at 9 p.m. from the chapter Ionic Equilibrium, which we are going to finish in this week. Yeah. And I'm sure you will be super excited for that as well. Yes. Okay. So, people, do like the video, share and subscribe the channel so that everyone will get benefited out of these sessions, which I always say in the every session. Yes. Chiranjeevi, yes, we'll be doing the atomic structure too. Yes, yes, absolutely. Alright guys, talking about the Vedantu JEE Pro subscription, let me tell you what all benefits you guys are going to get if you get enrolled in this Pro subscription. If you are taking this Pro subscription, what all benefits you guys are going to do. Let me tell you, you guys will be getting 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5 plus years of experience will be training you personally for the upcoming JEE 2021 as well as 2022, right? And you have got the option to learn either in English or in Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu. Yes. Okay, and people, at the end, we are going to cover everything, which includes your micro as well as crash courses. Okay, for the ones who are going to appear in JEE in 2021, we have come up with 3 different plans, as you all can see: 1 month, 3 month, and 6 month. On every plan right here, you have got 50% off, guys. Yes, the first plan, which is the 1 month plan, you guys are just getting it for 3750. 3 month plan 10.5k, 6 month plan 27k. On every plan right here, you have got 50% off. Yes, yes. And all these plans are valid for the ones who are going to appear in JEE in 2021. Now, for the ones who are going to write the JEE examination in 2022, we have again come up with 4 different plans, as you all can see. 1 month, 3 months, 6 months, 12 month. On every plan right here, we have got 50% off. And after the off, you guys are getting these for 2.5k, 6.75k, 12k and 21k respectively, right? On every plan, you have got 50% off right here, guys. Okay, and all these plans are valid for the ones who are going to write your JEE in 2022. Yes. Okay. How to get enrolled in it, how to get these pro subscription. Let me tell you guys, let me tell you how to get these plans. There's a link in the description box of the video. I want you guys to click on that link, use the coupon code as WBPRO. On using this coupon code of WBPRO, you guys are going to get the 50% off in whatever plan you are selecting for yourself. Okay. Hi Karthik, hi Vignesh, hi Sana. Welcome, welcome guys, welcome. Hi Wajid, thank you, thank you, thank you. Yes, Nishad, I remember you're my long-term student. Yes, I know, I know. Anurag, one shot revision भी होगा यार. Wait तो करो. अभी time है हमारे पास. Hi Harini. Hi Harshavardhani. Welcome to the session. Welcome to the session. All right, guys. So people, are you super duper excited for the Leachate principle? Let me know in the chat box. Let me know in the chat box with the thumbs up if you guys are super duper excited for this session. I think your Leachate principle will be getting explained by this GIF right here. What do you think? What do you think? Are you getting out of it? Are you getting something out of it? Are you getting something out of this? What do you think? The system right now is in equilibrium. Now equilibrium has disturbed. Now system is back to equilibrium. Yeah? What do you think? System is disturbed. It will again regain the equilibrium position. What are you thinking, guys? Are you getting something out of this? Let me know fast. Are you getting something out of this? See. Right now the system is in equilibrium. Yeah? Now I'm changing the equilibrium state. System is regaining its equilibrium. Yes? This is Leachate principle all about. This is Leachate principle all about. Yeah? Shift of equilibrium. Exactly, guys. So let's move on and talk about this Leachate principle in detail right here. Okay? See, guys, very simple concept it is, and I'll be using this concept in almost whole ionic equilibrium chapter. Okay? Exactly, Amir. You're right. See, according to this principle, as per its statement, according to this principle, if any change is imposed on the system, at equilibrium, then equilibrium will shift in the direction in which the effect of change is nullified. What does that mean? Whenever I'll be having any system at equilibrium, if you want to try to change the equilibrium state of the system, equilibrium always tries to regain its position. Yes, very simple. Okay, whenever I'll be having a system at equilibrium, if equilibrium somehow gets disturbed, if I want to disturb the equilibrium after that will try to nullify the change which was done on it. What does that mean? Simple, guys. Just look at this statement. Equilibrium does opposite of what we do to the reaction. This is something which I want you guys to remember. If you remember this, you're done. Whatever you will try to do with the equilibrium will try to do opposite of what we do to the reaction. Right? For example, I've got a reaction like this. Let's say A plus B in equilibrium with C plus D. Yes, let's assume the reaction right now is at equilibrium. Okay. Now, people, if the reaction is at equilibrium, if I'll try to do something on this reaction, equilibrium will just do opposite of what I do to the reaction. What does that mean? Have a look. If I try to increase the concentration of A, equilibrium will try to decrease it. How? It will lead the reaction to proceed in the forward direction. That's how equilibrium will do opposite of what I did. Yes. If, for example, I will increase the concentration of C. If I'm going to increase the concentration of C, equilibrium will again try to decrease it. How it can decrease the concentration of C? When it will make the reaction to move in the backward direction. Yes. Very simple. So whatever you are going to do with the reaction, equilibrium is going to do opposite of what you are doing. Yes. If you want to increase the pressure, equilibrium will try to decrease it. Yes. If you want to increase the concentration of reactant, equilibrium will try to decrease the concentration of reactant. If you try to increase the concentration of product, equilibrium will try to decrease the concentration of product. That's what we have to discuss in this Leachate principle in detail, guys. Yes. In detail. Yes. So in short, whatever we are going to do with the reaction, equilibrium just does opposite of what we do to the reaction. Correct? Let's get to know this concept a bit more in detail. Let's get to know what will happen to the equilibrium when I change the concentration, when I change the pressure, when I'll change the temperature. Okay, what will happen to the equilibrium state? Let's get to know that properly in detail, right? So I'm moving on to the first topic, guys, of this Leachate principle. What is that? That is the effect of addition of reactant or product. Correct? What is going to happen to the equilibrium? If I'll try to change the amount of reactant and product? See, guys, number one, if I'll be adding some reactant in this reaction which is at equilibrium, I'm assuming the reaction right now is at equilibrium. Yes. If I'll try to add some reactant, if I'll try to add some more reactant in the container in which this reaction is proceeding, yeah? This is the reaction which is taking place in a container right now, and this reaction right here is at equilibrium. So first of all, if I want to increase the concentration of reactant right here, what is equilibrium going to do? Equilibrium is going to decrease the concentration of reactant. How will equilibrium decrease the concentration of the reactant? When it will lead the reaction to proceed in the forward direction. Yes, very simple. At the same time, if some product is removed, if I'm decreasing the concentration of product, if I'll decrease the concentration of product, if I'll by chance decrease the concentration of product, equilibrium will try to increase it. How equilibrium will try to increase the concentration of product? When it will move this reaction in the forward direction. Yes. So remember guys, the first step, if more reactant is added or product is removed, reaction always shifts in the forward direction. I'm going to give you the logic of it as well. Okay. First of all, this is how we remember it. Now let's talk about the logic of it. Why it happens. Why it happens. See, what I told you, if more reactant is added, equilibrium will try shift in such a direction which decreases the concentration of reactant, and how equilibrium will be decreasing the concentration of reactant when it will make the reaction to proceed in the forward direction. If I decrease the concentration of product, equilibrium will again try to increase it. How? When it will move the reaction in the forward direction. Yes. So in both the cases, if more reactant is added or product is removed, if more reactant is added or product is removed, reaction is going to shift towards the forward direction. Now let's actually check why it happens. Let's get to know why it happens. See guys, I'm going to tell you the logic about it. See, first of all, the reaction right here is at equilibrium, okay? So can I say at equilibrium, reaction quotient is always equal to equilibrium constant? Yes. Reaction quotient of the reaction and equilibrium constant are equal when the reaction is at equilibrium. Yes. Both are equal. QC is equal to K equilibrium will be equal to concentration of product divided by concentration of reactant. Yeah? Yes. Now people understand. Now people understand what I'll be saying. If I will increase the concentration of reactant, if I will increase the concentration of reactant, yes, if I'll increase the concentration of reactant, can I say this term will decrease? Can I say this term will decrease? That means QC value is decreasing for this reaction. If QC value is decreasing, I told you in the last session, QC always tries to get equal to equilibrium constant. Yes. Now see, if I'm increasing the concentration of reactant, this whole term will decrease. If this whole term is decreasing, that means QC value is decreasing. QC value is decreasing. If QC value decreased, what will happen? QC value will again get back to K equilibrium. How? When it will increase its value. When QC will increase its value. And how QC will increase its value? When the numerator will increase and denominator will decrease. Numerator will increase. What does that mean? That means the concentration of product will increase. And how will concentration of product increase? When the reaction will move in the forward direction. Let me know in the chat box if you got the concept. Let me know in the chat box fast if you got the concept. Yes, very simple. Very, very, very simple. Now people, at the same time, one more thing at the same time. See, when the reaction was at equilibrium, QC was equal to equilibrium constant, which was equal to concentration of product divided by concentration of reactant. Yeah, this is something which we had. Now people, at equilibrium, QC is equal to K equilibrium. Absolutely. Now if product is removed, if the concentration of product is decreased, if I decrease the concentration of product, can I say this whole term will decrease? If this whole term is decreasing, that means QC value is decreasing. So QC will again get back equal to, QC will try to get equal to K equilibrium again. How will it increase its value? See, first of all, if I'm decreasing the concentration of product, this whole value will decrease. This whole value will decrease. That means QC value will decrease. Now, if QC value has decreased, QC will again want to increase its value such that its value becomes equal to K equilibrium. How QC can increase its value? If the concentration of product will increase and concentration of reactant will decrease. Yes. And how will the concentration of product increase when the reaction will move in the forward direction? Yes. Very, very, very simple. Let me know in the chat box if it's clear to everyone. Let me know in the chat box if it's clear to everyone. Fast, fast, fast. Yes. So remember, if more reactant is added or product is removed, reaction shifts forward. Very, very, very simple. Yeah. Talking about the second statement, guys, I'm sure you can easily kill this second statement now. If reactant is removed or product is added, if reactant is removed or product is added, that means if I'm decreasing the concentration of reactant or increasing the concentration of product. First of all, let's talk about this one. If the concentration of reactant is decreased, what will happen to the reaction? Understand. See, guys, first of all, if the reaction is at equilibrium, I'll say its QC will be equal to KEQ, which is going to be equal to concentration of product at equilibrium divided by concentration of reactant at equilibrium. Yes. Now, people, if I'm decreasing the concentration of reactant, when I'll decrease the concentration of reactant, can I say this whole value will increase? Yes. So QC value will increase. If QC value is increasing, but QC always wants to get equal to K equilibrium, but right here what is happening? I'm decreasing the concentration of reactant by means of which QC is increasing. But QC want to decrease its value. Why? Because it wants to get equal to K equilibrium. Yes. How QC will decrease its value? QC will decrease its value only if the numerator will decrease and denominator will increase. Numerator will decrease, that means concentration of product will decrease and concentration of reactant will increase. So how it is possible? How concentration of product will decrease? When the reaction will move in the backward direction. Yes. Let me know in the chat box if it's clear to everyone. Yes. Umar, मैं श्रीनगर में हूँ भाई. Let me know in the chat box if it's clear to everyone. Yes. Very simple. Correct. One more thing, guys. One more thing. Similarly like this. You can easily get it. If I'll increase the concentration of product, what is going to happen? Understand. See, first of all, let's say the reaction is at equilibrium, so its QC is equal to KEQ, which is equal to concentration of product divided by concentration of reactant. Yes. Now, people, if I am increasing the concentration of product, so this whole term is increasing. If this whole term is increasing, so QC is increasing. But QC always wants to get equal to K equilibrium. If QC value has increased, so QC will again get back equal to K equilibrium. How? When it will decrease its value. How it's going to decrease its value? When product will increase, reactant will when product will decrease, reactant will increase. How product will decrease? When the reaction will move in the backward direction. Yes. So remember, if reactant is removed or product is added, backward reaction always proceeds. Backward reaction is favored. Yes. Very simple. And people, there is a note which I want you guys to remember. There is no effect of adding a solid at equilibrium. Yes, because for solids, you already know their active masses are taken to be unity. Yes. Let me know in the chat box if everything is damn clear till here, so that we can move on and talk about few more interesting and fascinating things right here. Yes. Let me know fast in the chat box. Yes. Okay, wonderful, guys. I'm moving ahead and talking about few more interesting things right here. That is the effect of pressure, effect of change in pressure. If I'll change the pressure, what is going to happen to the equilibrium? Understand that as well. Okay. See, guys, what is written over here? On increasing the pressure, the reaction will shift in that direction in which the total gaseous moles decreases. What does that mean? Yes, Umar, I'll be teaching the organic chemistry soon, bro. Just wait for it. Now, people, see. On the reactant side, if I'll ask you how many moles do we have got 1 mole of N2 and 3 moles of H2. So 3 plus 1, 4 moles. Yes. On the product side, how many moles do we have? We have got 2 moles. Yes. So can I say when the forward reaction will be proceeding, number of moles are decreasing? Yes. If number of moles are decreasing through the forward reaction, so pressure will decrease due to the forward reaction. Yes. Now, people, if backward reaction will proceed, what is going to happen? Number of moles are increasing. If number of moles will increase, pressure will increase. This is something you should know right here. Yes. Now, people understand. If I'll increase the pressure, I am increasing the pressure, so equilibrium will try to decrease it. How equilibrium will decrease the pressure? When it will make the reaction to proceed in the forward direction. Yes. Very simple. Yes. So if I'm increasing the pressure, equilibrium is shifting the reaction in the forward direction. That means equilibrium is shifting the reaction towards the lesser number of moles. Okay. At the same time, if I'll decrease the pressure, equilibrium will again try to increase it. How will it be increasing it? It will make the reaction to proceed in the backward direction, because we know in the backward direction the pressure is increasing. Yes, very, very, very simple. Very, very, very simple. Yes. Yes. Let me know in the chat box if it's clear to everyone. Let me know fast. Let me know fast. Let me know fast. Yes. Wonderful, guys. Great. All right. So what you have to remember, see, on increasing the pressure, equilibrium moves in such a direction in which the number of moles decreases. On decreasing the pressure, equilibrium moves in such a direction in which the number of moles increase. Yeah. So this is something which I want you guys to remember right here. Correct? Now people, for the reaction which have got delta and G0, this is the reaction which has got delta and G0. On the left hand side we have got 2 moles, on the right hand side we have got 2 moles. Yes. So the pressure is same on both the sides. Yes. Yes. I can say like that. I can say like that. Correct? If I'll increase or decrease the pressure, what will happen to the equilibrium? Will the reaction shift in forward or backward direction? No way. There will be no shift right here for the reaction whose delta and G will be equal to 0. Yes. Yes. Very, very, very simple. Correct? Now guys, understand the actual thing which is very, very, very important. This is very, very, very important. Okay? Understand it properly. Okay? First of all, remember this equation. Remember this equation. Remember this equation. Now guys, see. For example, I have got a reaction as a reactant in equilibrium with product. Let's say this is one general reaction which I have right here. Correct? Let's say when the temperature of the reaction is T1, its equilibrium constant is equal to K1. Okay? Now I'm changing the temperature of the reaction from T1 to T2 and its equilibrium constant changes from K1 to K2. Okay? Yes, T1 is the initial temperature of the reaction at which the equilibrium constant was K1. T2 is the final temperature of the reaction at which equilibrium constant is K2. Okay? Now people, if I assume T2 is greater than T1, I'm assuming T2 is greater than T1. So what does that mean? That means I'm increasing the temperature of the reaction. I'm increasing the temperature of the reaction. Okay? Now people, if I increase the temperature of the reaction, if I increase the temperature of this process, first of all, it's going to be T2 minus T1 divided by T1 T2. Yes. So I can write this equation like this so that you can get it properly. This is log of K2 divided by K1. This is the equilibrium, this K2 is the equilibrium constant at temperature T2. K1 is the equilibrium constant at temperature T1. It's going to be simply equal delta H divided by 2.303 R. So I'm going to simply cross multiply it. It's going to be T2 minus T1 divided by T1 T2. I can write it like this. Absolutely, yes. Now people, what have I done? What have I done? I have increased the temperature of the reaction from T1 to T2. Yes, I have increased the temperature. If I've increased the temperature, that means T2 will be greater than T1. If T2 is greater than T1, can I say this value is going to be positive? This value is going to be positive. Yes, I mean this value is going to be positive. This value is going to be positive because I'm increasing the temperature of the reaction. So T2 minus T1 will be positive. Yes. Now guys, understand one important thing, very, very important, which is, okay, say, let's say I have got an endothermic reaction. Let's say I have got an endothermic reaction. Let's say I have got an endothermic reaction. Let's say the reaction which I took right here, it is an endothermic reaction. Yes. People, as you all must be knowing, for endothermic reactions, delta H is positive. Delta H is positive. Yes. And what have I done? I have increased the temperature of the system. I have increased the temperature of the reaction. So this value came out to be positive. Whatever is inside the bracket, it's going to come as positive. Since delta H will be also positive because the reaction is endothermic, right? This is positive. This term is positive. This term is positive. So can I say log of K2 divided by K1 to the base 10, it is going to be positive. Yes. So I'll say log to the base 10, K2 divided by K1, it is going to come positive. Yes. When is it possible? It's possible only if K2 divided by K1 is greater than 1. Yes. K2 divided by K1 is greater than 1. And what can we get from it? We can get K2 will be simply greater than K1. Yes. What is K2? K2 is the equilibrium constant at temperature T2. K1 is the equilibrium constant at temperature T1. Yes. So people, can I say on increasing the temperature for an endothermic reaction, its equilibrium constant also increases. the value of equilibrium constant increases. Let me know in the chat box if it's clear to everyone. For an endothermic reaction, on increasing the temperature, the value of equilibrium constant also increases, because we got to know it practically. Yes, K2 is greater than K1. Correct? Correct? Very simple, very simple. Yes? Yes? Now people, now understand one more thing. I'm sure this is clear. I'm sure this is clear. So remember, on increasing the temperature, equilibrium constant increases for which reaction? For endothermic reaction. For endothermic reaction. Correct? Now what is going to happen to the exothermic reaction? If I'll increase the temperature of the exothermic reaction, what is going to happen? Let's assume the reaction right here is exothermic. If it is exothermic, delta H value for the reaction is going to be negative, because we know for exothermic reactions delta H is negative. Correct? Now people, since I'm increasing the temperature, so T2 will be greater than T1. If T2 is greater than T1, this value right here is again going to be positive. Yes, but since it is the exothermic reaction, delta H will be negative. People, positive negative becomes negative. So I'll say right here log to the base 10 K2 divided by K1, it is going to be negative, right? It is going to be negative. When is it possible? When is it possible? Can I say it's possible only if K2 divided by K1 is less than 1? Yes. What can I conclude from it? I can conclude K2 is less than K1. So people, can I simply say for the exothermic reaction, if I'll increase the temperature, equilibrium constant is decreasing? Yes. Yes, I can say that. I can say that. For an exothermic reaction, on increasing the temperature, equilibrium constant decreases. Equilibrium constant decreases for which reaction? For the exothermic reaction. Now there is something interesting right here which you need to understand properly. There is something interesting right here which you need to understand properly. Okay, I'm erasing this part and I'll tell you something which is really important, which will make your concepts very clear. See guys, what I did, I took a reaction right here, reactant in equilibrium with products. Yes, when the temperature of this reaction was T1, its equilibrium constant was K1. When I changed the temperature from T1 to T2, its equilibrium constant changed from K1 to K2. Yes, and I'm increasing the temperature, T2 is greater than T1, correct? T2 is greater than T1. What I got right here, I got to know for the endothermic reaction, on increasing the temperature, equilibrium constant increases. And for exothermic reaction, on increasing the temperature, equilibrium constant decreases. Okay. Let's talk about endothermic reaction first. Let's see why it happens. Let's say what happens actually for the endothermic reaction. What I got to know on increasing the temperature, equilibrium constant increases. Yes, for the endothermic reaction. People, do you remember the equilibrium constant KEQ? It is actually equal to rate constant for forward reaction divided by rate constant for backward reaction. Yes, KF is the rate constant for forward reaction, KB is the rate constant for backward reaction. Yes, let's say the reaction which I took right here, it is the endothermic reaction. So its equilibrium constant will be KF divided by KB. Yes, and on increasing its temperature, what is going to happen to its equilibrium constant? Equilibrium constant will increase. Equilibrium constant for the reaction right here, which is endothermic, will increase if I'll increase its temperature. Yes, on increasing the temperature, equilibrium constant increases. Yes, what does that mean? If the equilibrium constant value has to increase for an endothermic reaction, on increasing the temperature, KEQ has to increase. What does that mean? Does that mean KF increases and KB decreases? Does that mean? Does it mean so? Does that mean on increasing the temperature, K equilibrium increases? Does that actually mean KF increases and KB decreases? No. No, guys. If you are thinking like this, you are absolutely wrong. If you are thinking like this, you are absolutely wrong. Remember, with the increase in temperature, rate constant, if it is for forward reaction or backward reaction, both increases. With the increase in temperature, rate constant for a reaction, be it rate constant for forward or rate constant for backward reaction, both increases. Then how come, if this is also increasing, this is also increasing, how come K equilibrium increases? Simple, guys. On increasing the temperature for the endothermic reaction, K equilibrium increases. K equilibrium increases. KF value increases as well as KB value increases. Yes, but people, increase in the value of KF, will be more than that of increase in the value of KB. Will be more than that of increase in the value of Kb. I want you guys to understand this, okay? So remember, for the endothermic reaction, on increasing the temperature, equilibrium constant increases, right? Equilibrium constant increases. Does that mean Kf increase and Kb decreases? No, both the values increases, because we know on increasing the temperature, rate constant always increases. If it is for forward or backward, rate constant is going to increase. But remember, increase in the value of Kf will be more than that of increase in the value of Kb. Therefore, equilibrium constant increases on increasing the temperature for the endothermic reaction. Yes? Let me know if it is clear to everyone. Let me know if it is clear to everyone fast. Yes? Wonderful, guys. Great. Now, talking about the exothermic reaction. Now, you people are going to tell me what is going to happen. See, guys. See. Now, you people will make me understand what is going to happen. See. First of all, I'm assuming this reaction to be exothermic. And we know for exothermic reactions, on increasing the temperature, equilibrium constant decreases. Yes. And already we know, on increasing the temperature, rate constant for forward as well as rate constant for backward reaction both increases. Yes, this is something which we know. Yes. Now people, for exothermic reaction, I told you, on increasing the temperature, K equilibrium decreases for exothermic reaction. Okay. Since K equilibrium constant, we know is equal rate constant for forward reaction divided by rate constant for backward reaction. On increasing the temperature for exothermic reaction, equilibrium constant decreases. Does that mean Kf decreases and Kb increases? Does it mean something like this? Does it mean on increasing the temperature of the exothermic reaction, K equilibrium decreases? Does it actually mean Kf decreases and Kb increases? No way. Why? Because we know on increasing the temperature, Kf as well as Kb increases. But right now on increasing the temperature of the exothermic reaction, K equilibrium has to decrease. K equilibrium has to decrease. But this is also increasing. But people remember, in the exothermic reaction, on increasing the temperature, increase in the value of Kb is more than that of increase in the value of Kf. That is why your overall equilibrium constant decreases. Let me know in the chat box if it is clear to everyone. Yes? Let me know in the chat box if it is clear to everyone. I hope this concept is clear to everyone, every single guy right here. Let me know in the chat box with the thumbs up if it's clear to everyone. Yeah? Yes? Let me know fast so that I can move ahead and talk about a few more things. Yes? Wonderful, guys. Great job. Great. Now people, let's talk about one more important thing. That is the effect of inert gas addition. At constant pressure. Correct? Since this is one homogeneous gaseous phase reaction. Right here. Correct? So people, you might be knowing this equation, PV is equal to nRT. So first of all, if I am keeping the pressure and temperature constant, R is already constant, can I say volume is directly proportional to moles? If I increase the moles, what is going to happen to volume? Volume will increase. If I decrease the moles, what is going to happen to the volume? Volume will decrease, as you all must be knowing. Yes? Now let's assume the reaction right here is at equilibrium. And these are the concentrations of each reactants and products at equilibrium. Let's assume this. Yes? And we know, guys, at equilibrium QC is equal to equilibrium constant Kc, which is going to be simply concentration of PCl3 B divided by V multiplied by concentration of Cl2, which is B divided by V, divided by concentration of PCl5, which is A divided by V. Can I say 1V is gone? So I got the value as B square divided by A multiplied by V. Yes, this is the value of equilibrium constant as well as reaction quotient when the reaction is at equilibrium. Yes. Now people, this reaction is taking place in a container. Yes, this reaction is taking place in a closed container, right? Now guys, understand one thing. If I'll add some inert gas right here, at constant pressure, I'm adding the inert gas at constant pressure. Since I'm adding the inert gas, what is going to happen to the total moles present in the container? Can I say total moles are going to increase? If total moles are increasing, what is going to happen to the volume? what is going to happen to the volume of the system? Volume of the system is going to increase. People, if volume is increasing, can I say QC value will be decreasing? QC value will start to decrease. But will QC try to decrease its value? See, what is happening? First of all, I'm adding the inert gas. On adding the inert gas, number of moles are increasing. So volume is increasing, volume of the system is increasing. If volume of the system is increasing, that means QC value is decreasing. If QC value is decreasing, always QC wants to get equal to KC. Yes. So QC should increase its value or decrease its value? QC should increase its value. Correct? On adding the inert gas at constant pressure, QC should increase its value, then only it will become equal to KC again. Okay, how will QC increase its value? QC will only increase its value if the reaction will proceed in the forward direction. Yes, if the reaction will be proceeding in the forward direction. So right here, on adding the inert gas in this container at constant pressure, if what is going to happen? The reaction is going to proceed in the forward direction. Yes. Let me know if it's clear to everyone. Let me know if it is clear to everyone. Yes. So this is something which is written here. On adding the inert gas at constant pressure, volume will increase and reaction shifts towards the highest number of moles, which actually happened on increasing the amount. On adding the inert gas in the container, the reaction proceeded in the forward direction. The reaction proceeded in the highest number of moles. Right? Over here we have got only 1 mole. Over here we have got 1 plus 1, 2 moles. So the reaction is shifting towards more number of moles. Is it clear? Yeah? Very simple it is. Wonderful. Great. Yes? So whatever you are doing to the equilibrium is just doing opposite of what we do to the reaction. Yes? Very, very simple. Now people, what is the effect of inert gas addition at constant volume? Let's talk about that as well. This was the effect of inert gas addition at constant pressure, and we got to know on adding the inert gas, number of moles are increasing, volume is increasing. If volume is increasing, QC value is decreasing, but QC again wants to bring back its value. It will again increase its value. How it can increase its value? When the reaction will move forward, and if the reaction is moving forward, that means the reaction is moving towards more number of moles. So whenever inert gas is added at constant pressure, reaction will always move towards more number of moles. Yes, very, very, very simple. Okay. Wonderful. Moving on, let's talk about the effect of inert gas addition at constant volume. Okay, this is the reaction which is taking place in the container, right? And the volume of the container is fixed, volume of the container is constant, volume of the system is constant, I must say. Yes, volume of the system is constant. Okay, let's assume there is the equilibrium in the reaction. Let's assume this reaction is already at equilibrium. If the reaction is already at equilibrium, can I say at that time its QC value is going to be equal to its KC value, equilibrium constant, or KP as well, right? Yes. At equilibrium, QC will be equal to equilibrium constant. And right here, which equilibrium constant I'm talking about? I'm talking about KP right here. Okay. Yes. Let's assume at equilibrium, when there is equilibrium in the reaction, I have got A moles of PCl5, I have got B moles of PCl3, and I have got B moles of Cl2 in the container when the reaction is at equilibrium. Let's assume that. Okay. People, if I'll ask you how many total moles I'll be having at equilibrium in the container, isn't it going to be A plus 2B? Isn't it going to be A plus 2B? This NT right here represents total moles in the container at equilibrium. Yes. Now people, if I'm dividing these moles by the total moles present in the container, can I say this term is going to give me the mole fraction of PCl5 at equilibrium? Can I say this term is going to give me mole fraction of PCl3 at equilibrium? Can I say this term is going to give me mole fraction of Cl2 at equilibrium? Let's assume total pressure at equilibrium in the container is equal to P. I'm multiplying this by P, I'm multiplying this by P, I'm multiplying this by T. Can I say this whole term now is going to give me the partial pressure of PCl5 at equilibrium? Can I say this whole term is going to give me the partial pressure of PCl3 at equilibrium? Can I say this whole term is going to give me partial pressure of Cl2 at equilibrium, right? So if I want to write the expression for Kp, this is going to be equal partial pressure of this at equilibrium multiplied by partial pressure of this at equilibrium divided by partial pressure of this at equilibrium, which is going to be at the end, you can check it out, it's going to be B square multiplied by Pt. Pt is the total pressure of the container at equilibrium multiplied by A multiplied by Nt, where Nt represents the total moles present in the container at equilibrium. Yes, and Pt represents the total pressure of the container at equilibrium. Yes. Now people, what am I going to do? First of all, this is the reaction which is taking place in a container, as you all must be knowing. correct? The walls of the container are rigid. There will be no effect on the volume. Volume of the system is not going to change, correct? Now, if I'll add some inert gas in this container, since volume is not going to change, if I'm adding some inert gases in the container, can I say total moles present in the container are increasing? So total moles present in the containers are increasing. At the same time, if the moles are increasing and volume is remaining constant, can I say total pressure at equilibrium will also increase? I mean, can I say total pressure is also going to increase? So this term, NT is increasing, PT is increasing, and whatever will be the magnitude of increase in the value of NT, same is going to be the magnitude of increase in the value of PT. So there'll be no effect on this case QC over here. There'll be no effect on this equilibrium constant right here. Let me know in the chat box if it's clear to everyone. So remember guys, on adding inert gas at constant volume, there'll be no effect on the equilibrium state. Why? Because whatever will be the increase in the value of PT, same is going to be the increase in the value of NT over here. Let me know in the chat box if everything is clear right here. Yes? Wonderful guys, great job done. Now the last point, after that I'll be giving you one question. With that things will get again very clear to you, okay? Effect of catalyst, right? What is the catalyst? Catalyst is the substance which alters the rate of the reaction, which alters the speed of the reaction, okay? It can speed up the reaction, it can increase the speed, or it can decrease. Right now I'm talking about the positive catalyst, which is going to increase the rate of the reaction, right? But remember guys, a positive catalyst increases the rate of forward as well as backward reaction. A positive catalyst increases the rate of forward as well as backward reaction, okay? And it increases the rate of forward and backward reaction by the same amount, okay? So remember guys, on adding the catalyst, it does not affect the equilibrium state. It only changes the time taken to attain the equilibrium state, right? It only changes the time taken to attain equilibrium in the reaction. It is not going to do anything with the K equilibrium value. K equilibrium is not going to change on adding the catalyst. It's only going to change the time taken to attain the equilibrium. Yes, very, very simple concept, right? Hi Ankit, good evening. Hi Nikhil. Hi Gazanfar. Yes? Jumana, negative catalyst is the one which decreases the rate of the reaction. Yeah? Wonderful guys. Okay, I'll be giving you one question at the end, and with this question I'm going to end today's discussion. If you got this question correct, that means your concepts about Leachate layer principle are clear. If you didn't get it properly, that means your concepts about Leachate layer principle are still not clear, right? I want you to give it a try. Predict the direction of shift of equilibrium, okay? The reaction I have, that is N2 gas, understand properly, that is N2 gas plus 3 times H2 gas in equilibrium with, and right here I'm giving some 100 kilojoules of energy, right here I'm giving some 100 kilojoules per mole of energy, right? So the reaction right here in this case is endothermic, yes, but actually if we talk about Haber's process, this reaction is exothermic, but this is the hypothetical case, yeah? This is the hypothetical case. First of all, if more H2 is added, let me know fast what will happen. If more H2 is added, if I'll be adding more H2, equilibrium will try to decrease the amount of H2. Yes, whatever we do to the reaction, equilibrium just does opposite of what we do. Yes? Yes, very simple. If I try to increase the amount of H2, equilibrium will try to decrease it. How will it be decreasing it? When it will make the reaction to proceed in the forward direction. Yes. So first question, equilibrium will move in the forward direction. Yes. Yes. Right? Very, very, very simple. Nikhil, bro, this is the last session of Chemical Equilibrium. Go to the first session and watch this series of the lectures. You'll get to know what equilibrium is all about. Yeah, Nikhil, you can do that? Exactly. Now, people. Now, talking about the second one. If NH3 is added, if I'm adding some NH3, if NH3 is added, if I'm adding some NH3, equilibrium is going to do opposite of what I do. If I'm adding some NH3, equilibrium will try to decrease the amount of NH3. How equilibrium will be decreasing the amount of NH3? When it will be making the reaction to proceed in the backward direction. So right here, which reaction will proceed? Backward reaction will proceed. Yes. Yes. Very, very, very simple. Correct? Now. See, right here, if temperature is inversed, it's not inversed if temperature is increased. If temperature is increased, what is going to happen? See guys, see, understand. First of all, is this right now endothermic or exothermic? Is this endo or exo? What do you think? Is this endo or exo? This is endothermic reaction because I'm supplying energy. Yes, it is endothermic reaction. For endothermic reaction, people, we discussed in detail right now with the increase in temperature, what happens to equilibrium constant? Equilibrium constant increases, right? If equilibrium constant increases, that means the reaction will be moving in the forward direction. Yes. Exactly, guys. Exactly. All of you are perfect. Right now. See, when the temperature is increased, for the endothermic reaction, equilibrium constant increases. And if equilibrium constant has to increase, that means the reaction has to move into the forward direction. Yes. So right here, the reaction will be moving in the forward direction. Okay. If inert gas is added at constant volume, what will happen? Tell me guys in the chat box, what will happen if inert gas is added at constant volume? Let me know fast. Will there be any effect? Just now, few minutes back, we talked about the inert gas addition at constant volume. There'll be no change in the equilibrium state. Yes, there'll be no effect at all. At constant volume. Yes. Okay. What is going to happen if inert gas is added at constant pressure? What is going to happen? See, on the reactant side, I've got 4 moles. On the product side, I have 2 moles. If forward reaction will proceed, number of moles are decreasing during forward direction. So pressure is decreasing during forward reaction. And during backward direction, pressure of the system is increasing. Yes, this is something which we already know. Correct? Now people, if inert gas is adding at constant pressure, if I'm adding inert gas in the same container in which this reaction is proceeding, can I say number of moles are increasing? If number of moles will increase, can I say pressure will increase? So equilibrium will try to decrease the pressure. How equilibrium will try to decrease the pressure? When it will make the reaction to proceed in the forward direction, because in the forward direction pressure decreases. Yes. So I would say in the last case, the forward reaction is going to proceed. Let me know in the chat box if everything right here is clear to everyone or not. Let me know, guys. With this, our chemical equilibrium is done and dusted. Tomorrow, we are going to start the ionic equilibrium. Let me know in the chat box, guys, if every damn thing is clear to you or not. Let me know fast. Yes. That's great, Jumana. That's great. Hi, Ananya. How are you doing? You came late. Yes. Wonderful, guys. So this was all from my side. I'm going to end the session like 5-10 minutes early today because our topic is done. Yes, I'm sure you would have loved the session. You would have enjoyed the Leachate layer principle. Yes, and I'm going to use this Leachate layer principle everywhere in the ionic equilibrium, guys. So do not miss the ionic equilibrium sessions from tomorrow. I'm starting the ionic equilibrium, which is one of the most important chapters as per your chemistry is concerned. Yes. Giovanna, next is ionic equilibrium tomorrow, which I'll be taking, right? At the same 5:30 time. Okay? So people, you take care. Bye-bye. God bless you all. Love you all. I'll see you guys tomorrow at 5:30. Take care. Bye-bye, guys.